Great. All right. And so we are recording. And so do tell your fellow classmates that the recording will show up sometime on that Zoom page tonight. All right. So let's get started. I'm going to start on chapter 21. So nuclear chemistry. We went through some coordination chemistry here in class, but I would like to go over a little bit of the new material within here with nuclear reactions and review some of those things that we didn't review in previous sessions. So once we do chapters 21, and then we'll go to electrochemistry 20, keep in mind or take a note of what questions you want me to work on from previous midterms, or I'll answer any questions or try to do example questions that you guys have for me from previous chapters. All right, so chapter 21, nuclear chemistry. This is a little bit different. We're looking at chemical reactions pertaining to the subatomic particles in the nucleus of our atom. So mainly we're worrying about our protons and neutrons. So do understand how we get the number of protons and neutrons given a element name here, such as radium-226. So radium tells us what element it is. And since we know we have our periodic table, we know how many protons radium has. And so that second number there is the mass number. Mass number meaning the sum of the protons and the neutrons within that nucleus. So that number right there, our mass number, tells us our number of neutrons. It doesn't have 226 neutrons. It has 226 minus the number of protons there are number of protons there are, and that will give you the number of neutrons. All right, and so with nuclear chemistry, this is kind of a big step away from what we've talked about, in all of chemistry. We're not really so much focused on electrons here, so charge is not as important to balance these questions. So in this question, it's asking what product is formed when radium-226 undergoes alpha emission. So note the words here. It tells you what is your products and what is your reactants. So once you have your products and reactants on the correct side, given what is expressed, so alpha emission means that an alpha particle is being emitted. So we need to know that an alpha particle is just a helium nucleus. Sometimes we write helium, or we can write the alpha particle symbol. They mean the same exact thing, where there's 2 protons and 2 neutrons in the nucleus. The 2 neutrons right here is denoted by the total mass number is 4. So remember, mass number means protons and neutrons within there. And so since an alpha particle is emitted, this implies that an alpha particle is the product. So if we write our generic excuse me, balanced chemical equation, butterfingers, our generic chemical equation, we know that a alpha particle will be our product because it's being emitted. And so our radium-226 within here is going to be our reactant in this case. So excuse me, there is our reactant, and so 226 is our mass number. All right, and so we look at the periodic table to see where radium is. So radium is Ra. I think this is like oftentimes confused. Radium is Ra. Rn is radon. They both basically have, the majority, the same letters in their name. And I feel like those two could easily be confused since you are given a periodic table that does not have names on there. So do know that radon is Rn, it's element number 86. So 86 protons, while radium has 88 protons. So I like to write the number of protons also within our balanced chemical equation, because we know that mass has to be conserved here. So if we add up our numbers or think, okay, what's the missing piece that needs to be there, then we can identify the element that is the product. So I recognize that we are taking 2 of those protons to form that alpha particle. So 86 goes there within our product, and then what's it? 226 minus 4 is 222. All right, so this element is radon. So Rn, that would be our product there. And so what you see here is the trend that alpha emission, typically your element identity goes down by 2 atomic numbers, and your mass number goes down by 4. But you can tell that from the balanced chemical equation that you write. All right, so other nuclear equations that we can write, mercury 201 undergoing electron capture, and then we have thorium decaying to something else. So again, we're using the same strategy here, just figure out what is your reactant, what is your product, fill in the mass number and proton number values and balance it and see what is the missing piece. So for this first one, A, where we're undergoing electron capture, this is the only nuclear equation that the I guess like emission or like the radiation involved here is actually a reactant. So electron capture, your reactant is capturing an electron. An electron has no mass, but it has a charge of -1. So we put a -1 where the number of protons would go, because an electron is a -1 charge. So the idea here for electron capture, and this is different from all of the other nuclear reactions we have, this is actually a reactant. And our mercury 201 is also a reactant, because that's the species that is involved in this nuclear reaction. So both those things are reactants. So we just figure out, okay, if we add up all the numbers, make sure that they balance, what is the product that's formed? So mercury is Hg, right? It's 201, that's the mass number. Mercury is element number 81 protons, and we are capturing an electron, and this is a reactant. And so we draw our arrow and just think, okay, let's make sure everything balances here. So 81 minus 1 is 79, and our mass number here does not change. And so we look at what is element 79. It is gold. So with this reaction, we made gold, what alchemists were trying to do for hundreds of years. So it wasn't through chemical reactions that you can make gold, but I guess you can. If you undergo nuclear reactions, you can, achieve what alchemists were trying to achieve for, hundreds of years. So that's kind of neat there. So that one's done. All right, so B is a different substance. So we have thorium here. I'm not telling you what the emission or what type of radiation is involved here. So we need to figure that out, but it's still the same strategy. Just figure out what is the missing piece. So we're starting with thorium 231. That is our reactant. Thorium is element 90. And this substance is decaying, meaning that something is being emitted from it. And so we know that we are forming protactinium. So I need to figure out where that is on the periodic table. So that is element number 91 with the symbol Pa. And it is decaying to protactinium 231. And so we just need to figure out, okay, what's that missing piece? That would give us those balanced numbers. And so when I see here, what's different are the number of protons. So if I have a -1 charge here within the proton placement here and a 0 mass number, this would be balanced. And so from these numbers, I can recognize, oh, this is actually an a beta particle. All right, so I put an electron, initially, but what this is essentially a beta particle. All right, oh, yeah, beta particle emission within there. All right, so that's balancing nuclear reactions. Note that we basically ignored number of electrons. They're not really involved within here. We're just looking at the protons and the mass number or neutrons within these species. We're basically ignoring any charges that would be over here. We're assuming it's all neutral within there. All right. Okay, so let's keep going, where we talk about other types of nuclear decay. So here we want to predict the modes of decay for these different substances. So we can predict modes of decay using the belt of stability here. So my approach to this question, my strategy is calculate the neutron to proton ratio of these compounds. And depending if it's above, like way above or way below the belt of stability, certain decay modes are more common. So if we're above the belt of stability, so you note that I've pulled out what the book has, but from this belt of stability, what we should know is that elements that are above all of these blue dots. So the belt of stability is not this red line. This red line is just showing, okay, what is a 1-to-1 neutron to proton ratio? What we see here is that the belt of stability starts to deviate away from that 1-to-1 ratio as elements get really, really heavy. When they're really light, they're basically on the 1-to-1 ratio of neutrons to protons, but once it gets heavier, it goes up. So for example, bismuth, our heaviest, most stable element, its proton ratio is, neutron to proton ratio is 1.5 something. So 1.5 neutrons for every 1 proton. But really light elements such as oxygen, which is doubly magic number, so it's a very stable nucleus with 8 protons and 8 neutrons. Within there, its neutron to proton ratio is 1 because it's a very, very light element. So anyway, so when elements are fairly heavy, these substances tend to undergo beta emission. And that's how the substance can lower its neutron to proton ratio, because beta emission, you're converting a proton to a neutron. Or no, the other way. No, sorry. Yes, a neutron to a proton. So what that does is lower that neutron to proton ratio. So just remember that your beta particle has a -1 where the proton number goes. When we're below the belts of stability, oftentimes we will undergo positron emission or electron capture. You get the same result within there. So you get positron emission. All right. And doing that, you convert a proton to a neutron. And so in doing that, you raise your neutron to proton ratio. So understand that a positron emission is 0 and +1, and that is being emitted. So our strategy here, given these different isotopes, let's just calculate those neutron to proton ratios. So for carbon-14, it's in our best interest to figure out how many protons and neutrons there are. Carbon is element number 6, so there's 6 protons. So based upon the mass number given, there are 8 neutrons and there are 6 protons. So our ratio that we have here is, if you do that, it's 1.33. Okay, so based upon that number, it's way above the belt of stability. It should be 1. It should be close to 1, should be 1, because it's a pretty light element. So I don't need to give you the belt of stability here. You should know that because carbon is a light element, that it would prefer the most stable nuclei will have a proton to neutron ratio around 1. So this implies that this isotope will most likely undergo beta emission in order to lower its ratio. So why don't we just write what that would be? Because we've answered the question that carbon-14 will most likely undergo beta emission. But for fun, let's just write what that is, that full balanced chemical nuclear equation, just for completeness here. So if carbon-14 is undergoing beta emission, we are emitting a beta particle, which is 0, -1 within there. So the missing piece here, I need to have 7 protons in order for these two numbers to equal 6. And then our mass number does not change. And so based upon the number of protons, I recognize that that is nitrogen. So nitrogen-14. And actually, if you calculate the neutron to proton ratio for the product that we form here for nitrogen, it's 7 neutrons, 7 protons. So that equals 1. So when carbon-14 emits a beta particle, it forms a very, very stable nitrogen, a nitrogen nucleus. And so that's kind of interesting here. We talk about carbon dating, carbon-14 dating, that nitrogen is formed when it decays. So when we're talking about like the decay, radioactive dating here with carbon-14. It's not decaying to another carbon isotope. It's actually decaying to a nitrogen isotope that doesn't have radioactive properties at all. So that's the product within there. So let's do the other one, B, where we have xenon 118. So xenon is element 54. So our neutron to proton ratio, so we have 54 protons. So just figure out how many neutrons there are by subtracting those, the mass number there. So there are 64 neutrons present in that nucleus. And so if you calculate the ratio, it is 1.19. So 1.19 is pretty low. Xenon is a fairly heavy element. So this is, based upon the belt of stability here, what you see is that heavier elements, deviate away from the 1-to-1 ratio, where our heavy elements, bismuth or even iodide here, kind of in the middle within there, has a neutron to proton ratio of 1.4. So xenon is pretty close to iodine, so 1.4 should be the most stable neutron to proton ratio. So I recognize that this number is pretty low. So probably what's going to happen is positron emission or electron capture. Either of those will bring that neutron to proton ratio up closer towards the belt of stability. So we can write that. So in the key, I have positron emission, but let's write what the equation would be for electron capture for fun. All right, so electron capture of this xenon isotope, electron capture would be a 0, -1, we're capturing that electron. That would be the symbols for an electron there. And so the element that we make is going to have 53 protons, and our mass number doesn't change. And so what we create is I within there. So if we calculate the neutron to proton ratio for iodine here, it's a 1.23. So it's still not very high. This isotope will probably still undergo more emission to get to a more stable value, but that's not what this question asked. It just said, what does this, xenon isotope, what decay pattern does that one undergo? And so if you compare the answer we got here for electron capture versus positron emission, you'll note with emitting a positron, you actually get the exact same product as well. It would be our iodine with 118 mass number within there, that the product is exactly the same. All right, so there we go. So that's balancing equations. So what else we talked about in nuclear chemistry was the idea of, okay, these decays happen with a certain rate constant, and all decay, radioactive decay kinetics are first order reactions. So this is kind of a little bit of a review of chapter 14. It's all the same stuff. It's all the same stuff where we think about these decays and their kinetics in terms of their rate constants, but oftentimes what nuclear decay patterns they're talked about in terms of their half-lives. And so half-life is related to our rate constant through the equation T1/2 equals natural log of 2 over the rate constant. So this is given to you on the supplemental handout or the scratch paper that you'll be given. But I don't tell you which one is the first order half-life calculation. That you need to recognize which one on there that is, because you'll actually see 3 different half-life relationships between K, your rate constant, and your half-life, but only one of them is first order. And so that's the one we want to be using for these different reactions. So given this information that we have in our T1/2, we can relate our half-life that is given and the rate constant. And that's important because in some questions where we need to use the integrated rate law and not like a T1/2 calculation, we need to use K in the integrated rate law, not the half-life value. So the integrated rate law for first order reactions is this, and it's with the natural logs on that scratch paper. So do recognize that we can determine, okay, if we know how much we start with, we know the rate constant given the half-life, we can figure out how much is left. So sometimes we need to use this equation to calculate those concentrations. So given the information, so let's actually do the question now, because now we have all the equations we need. All right, so the half-life of cobalt-60 is 5.27 years. So that's our T1/2 value. That is not K. It's the half-life. It's the amount of time it takes this sample to reduce to 50% of what it started with. So if we start with 1 milligram of sample, so to me, that sounds like our initial concentration or our initial amount. How much is left after 15.81 years? So this is our time. This is actually how much time has elapsed. There are two ways to do this question when it is a first order reaction. The first way you can do it is just figure out how many half-lives have passed given the amount of time elapsed. Did I do it that way? Yes, I did. Yes, so in the key, I show you the two ways to do it. So the first way is just to consider how many half-lives have gone by. So if I start if 15 years has gone by and the half-life is 5.27 years, that means that how many half-lives have gone by? 3. Is it exactly 3? Wow, I made it easy. Okay, 3, not years. It's 3 half-lives have gone by. Even if this number wasn't a whole number, all right, if it wasn't like a whole number, it's still this next equation that I'll do next, it still works. So 3 half-lives, you can think, okay, after 1 half-life, your sample reduces to 50%. After another half-life, your sample will reduce to another 50%. So you'll have 25% left. And then after your third half-life, that 25% will have again. So it's 12.5%. So after 3 half-lives, you will have 12.5% of your sample left. So kind of like the cheater way. This is how I teach it in 1110 to make it like easy. I'm not going to teach them the integrated rate law in 1110, but how I teach it to them is that your isotope remaining, after the time that has elapsed equals what you start with initial, and I can spell initial, times 1/2, or the halving action here to the exponent of how many half-lives have elapsed. So, setting all of this up, it would be the amount we have left is 1 milligram times a half to the third power. So this is basically, if we rewrite it, that what's happening is I'm doing 1 milligram times a half times 1/2 times 1/2. And that's how we get that 12.5% that's left over. And so I think the answer that you get here is that 0.125 milligrams is left. So 25% of that milligram amount is left over. So this strategy that I did right here will work whatever time we started with. So for example, if instead of 15 whatever years, if I said 10 years, all right, so 10 divided by that number would be 10 divided by 5.27 is 1.897 half-lives. So it's not like a whole number of half-lives. We can't just say half or whatever. This equation still works. This is still equal to n, and you could put it in place of that exponent. So we just take 0.5 to the 1.897, and this equation will still work even if it's a fraction of half-lives. So the other way to do this equation, to do this problem, would be to use the integrated rate law instead, where we need to convert our half-life that's given. So the other way we can do it, I'm going to give myself another page, add a page, because I write too big. All right, so the other way to do this equation is, or this question, is to use the integrated rate law. The integrated rate law will always work. So this way that I showed before, this is kind of like my cheater way to do it when given a half-life time and an amount of time that has elapsed. And so the other way to do it, and again, it'll always work, is recognize that T1/2 equals natural log of 2 over K. So if we get that K value, we can plug it into our integrated rate law. So ln concentration times the initial constant, or minus the initial concentration, equals negative KT. So recognize that in this equation, we don't put the half-life time, we put K, the rate constant. So if we move things around and we get that K is equal to natural log of 2 over T1/2. That T1/2 is that 5.27 years. And so what we get is that K, our rate constant, is 0.131 years to the -1. Right, in order for the units to work out. So that's the K value that I'll put into my integrated rate law. T is the amount of time that has elapsed given the question. So 15 point, what is it? 15 point something, 15.81 years. All right. And then our initial concentration is 1 milligram. So we are calculating for the amount left. So A subscript T. So when you plug in all those things and solve for A subscript T here, that's how much is left. And you actually get the exact same number. So I like to, you can do this on your own and recognize that you get the same exact number. So the great thing about this equation is, as long as you know K, your rate constant, you can plug in any number for T, time elapsed, the actual time elapsed, given the question, given the information in that question. All right, so that was kind of a pretty straightforward radioactive decay question. It's the exact same as chapter 4. It's the exact same as 14. When we have time, when you have a time, for example, like 3 hours and 30 minutes, of course, yes. So if you need to make sure when that your units match here, and that's the same thing for chapter 14 with rates. If K, your rate constant, is in years, and the T is given in like months or something, you need to make sure that your time units match here so they cancel out. Or if you are doing it the cheater way, and let's say the half-life is given in minutes, okay, that like a substance takes 10 minutes to decay and I give you hours, it would be best to convert hours, the time that has actually elapsed, to minutes first, so you can get that ratio. So so that's a good point. Make sure that your units match. Okay, very good. All right, so let's do one still involving radioactive decay, but I just give you different pieces of information. And so recognize it's just chapter 14, just asked a little bit differently. Okay, so this question, if we start with strontium, 1 gram of strontium 90, and only this much, so 0.953 grams remain after 2 years, what is the half-life of this substance? So in this question, we cannot use the cheater, this equation. We can't use this equation because we're trying to figure out, okay, how many half-lives have, passed during this time. We would have to be solving for N in this case because we know how much we start with and we know how much remains. The problem is that there's really no way to calculate N unless N was like an integer number. If N is a fraction or, has decimal places in there, we can't actually solve for N given this formula, but we can use the integrated rate law. That always works. So we just need to recognize, what are the pieces of information given in this question that we can plug in. So I'll just start with the integrated rate law here. So natural log of what's remaining minus what we start with equals negative KT. So looking at this information given, we start with 1 gram. So that to me sounds like initial concentration. The 0.953, that's how much is left after some time. So that's A subscript T. And then it tells us how much time has elapsed. So T is 2 years in this case. So I guess the, confusion that might happen is that, oh, I give you years, the half-life of this substance is 2 years. But that's not true, because if you look at the amounts here, we didn't undergo a whole half-life, only just a tiny, tiny fraction of our substance decayed. If what was remaining was half a gram, then yes, the time amount would be the half-life, because that's how much, half the sample elapsed. So the best thing to do here is plug in all of these numbers that are given. T is 2 years, and solve for K within there. So I'll plug in everything. Natural log of 0.953 grams minus natural log of 1 gram equals negative K. That's what we're solving for, 2 years. And so you can see we are just solving for K within here. And just like your time units matching, you need to make sure that your units of concentration are also matching. If I give you a percentage, like let's say I rewrote this question and I say, you start with strontium and it decays, it loses 25% of its mass lost. So if the question was worded this way, then you would have to kind of do a little bit of reading comprehension here and recognize that you started with 100%. And after some time, if you lost 25%, then what you have left is 75%, right? And so you would be putting 100% in for a subscript 0 for your initial concentration. And then, oh, mom, no, my mom's calling me. Decline. Okay. Sorry about that. My mom called me. Sorry, mom. All right. What was I saying? Okay. Yeah. So if it was worded this way, if you lost 25% of strontium, what's implied is you start with 100%. That's A subscript O. And then what you have left is 75% of your sample. And that would be A subscript T. And then you would solve it the same way if we know how much time has elapsed. So anyway, let's go back to the original question, what was given, where I just give you masses. So it's essentially plug and chug here. So we solve for K. All right, so K in this case is 0.02407 years to the -1. All right, this is not our answer because we want the half-life of the substance. So half-life is our T1/2. And so just one small extra step at the end here where we take that K we just got and do natural log of 2 divided by that K value we just got. So 0.02407 years to the -1. And so natural log of 2 is like 0.693. I think that's what's given on the supplemental handout, but I just remember it's natural log of 2. And so this will be our half-life value, and it will have the unit of years because in the denominator we have year to the -1. So if we're taking something to the -1, it's on the denominator, it becomes years to no -1 exponent that comes out. So we see that T1/2 when you do this is about 28 years. So it would take 28 or 29 years for this strontium sample to reduce to 50%. So A subscript T would be 0.5. What do you do with the negative sign? The negative sign where? Like in here in the integrated rate law? Oh, you want to just isolate K. So this is, so I won't skip. So I'll just do the steps here. So natural log of this number, natural log of 0.953 is -0.0481. Natural log of 1 is 0. equals negative K 2 years. And so I divide both sides by -2 in this side. So I just want to calculate K. All right, so that negative sign needs to go onto the other side of the equation. All right, so that's how I got my answer. And that would be K. It would be, excuse me, negative 0.0481 divided by -2. And so this whole thing would be a positive number in that case. Oh, why is it year to the -1? Because natural law, so the first idea here is that we know this is a first order reaction. And so if you recall the units, you can figure out what the units of K tell you the order of the reaction, depending on where concentration is within the unit and where time is. So with a first order reaction, the unit is always time to the -1. The reasoning is because when you take the natural log of numbers or like any value here, it's unitless. So I need to make sure that this side of my equation is also unitless. So in order for this to be unitless, K needs to have the unit year to the -1 because T is years. And so that's how you make it become unitless. All right, and you'll see that for all of these, that the half-lives for specifically radioactive decay is always the time. K is always the time to the -1, or like some type of time unit to the -1. Therefore, when you plug it into your T1/2 equation, because K is always in the denominator, then what comes out is a time without an exponent on it. So whether it's year to the -1/2, second to the -1/2, you'll get an actual time that comes out. So that is specific for just first order reactions. And because all radioactive decay is first order kinetics, then that works within there. Okay, so there we go. Okay, so B, I need more space because I write too big. Okay, so B is how much strontium will remain after 5 years. Okay, so we just got K, so all we have to do is plug in a new integrated rate law equation and just plug in a brand new time here. So I'm going to be lazy and just copy this. All right, so I'm going to just copy this equation. We have K now, and we're changing the time. And so what we're calculating here is how much is left. So our initial concentration stays the same. We're still focusing on the 1 gram of the radioactive substance. Initially, we're just changing the time that's involved. So it's 5 years now. So we are plugging in K that we just got. We're not plugging in T1/2. We're plugging in the K value, so 0.02407 year to the -1/2. And so what you see here, sorry, it's all crammed up, but when you do this multiplication, you see that we have year to the -1/2 times a year. That gives us a unitless value that matches the unitlessness on the other side of the equation here. So we calculate this, and so know that natural log of 1 is 0. And so when you multiply these things together, you get 5 times that, 2407, you get equals -0.12035. It's unitless, natural log of A subscript T. And so since we are solving for A subscript T, we need to take both sides to the E to undo that natural log. And so we get A to the, how much isotope is left is 0.887 grams is left. Okay. And a way to check yourself is if you do all this work and you get a mass that is heavier, all right? Like if you do all of this and you notice that you're left with 1.2 grams is left, that probably means you forgot the negative sign. All right. Also use your intuition here a little bit, that your substance is decaying. You're starting with 1 gram and it's decaying. So you're losing your radioactive substance, that the mass needs to go down. So again, if you see a number and it goes up, then that kind of take a step back and relook at your work and make sure that, you're taking into account all the negative signs. If the mass goes up, that shouldn't make sense. Your substance is losing mass within there, that your substance, it's decaying. It shouldn't be going up in mass. That would not be decay. So if you see that your mass goes up, probably what happened is you forgot that negative sign. Okay, so there we go. That is chapter 21. Yeah, yes. Okay. So let's move on to chapter 20. 20. Oh, nope, 20. Okay. So chapter 20 is our redox reaction, so electrochemistry. So we are going back to thinking about electrons and where they're moving within a chemical reaction. And so how we predict spontaneity of redox reactions, so electrons, being transferred between products and reactants, that's a redox reaction. We look at their cell potentials. And so in this question, I give you a balanced redox reaction, and I want you to identify what's being oxidized, what's being reduced, what's the anode, what's the cathode. So basically, with this question, my strategy here is to determine the oxidation numbers of all of the reactive species, the things that are changing. And once you determine those oxidation numbers, you can figure out what substance is being oxidized, what's being reduced, and then therefore you can determine what is the cathode and what is the anode. So looking at oxidation numbers here for our substances. So recall the rules for oxidation numbers. Oxygen typically has a -2 oxidation number when it's in a compound. If it is like oxygen gas, then oxygen has an oxidation number of 0. But in this case, because oxygen is attached to things, it has an oxidation number of -2. So chromium in this case, if you balance all of those oxidation numbers, if oxygen is -2, there's 7 of them, so that's -14. But it's a -2 charge ion overall. So that means positive 12 has to come from the chromiums. And since there's 2 chromiums, they kind of split the positive charge here. So just 1 chromium atom is a +6 oxidation number, all right? And so what we see here also is that iodide is this free ion. So its oxidation number is just equal to its charge because it's just a simple like monoatomic ion within there. So chromium in dichromate here is a little bit more complex. Hydrogen also has a +1 oxidation number because it's just a monoatomic ion here. When we go to the other side, what we see here is that we have oxygen attached to hydrogen. So those oxidation numbers are +1 and -2 in order to be charge neutral. So what you recognize here is that the oxidation number of hydrogen is not changing and the oxidation number of oxygen is not changing. So the important species here are all the other weird things other than hydrogen and oxygen. It's actually chromium and iodine. So we're not looking at those substances, hydrogen and oxygen, because their oxidation numbers aren't changing. But if we look at chromium, we see the oxidation number does change. It goes to +3, and iodine, because it's a neutral element, has the oxidation number of 0, just like diatomic hydrogen, diatomic oxygen, nitrogen, all of those have 0 oxidation numbers. So to figure out what's being oxidized and what's reduced, we're just looking at the substances that are changing oxidation number. So like I said, hydrogen isn't changing, oxygen isn't changing, so we ignore them. But when we look at iodine, we see that its oxidation number is actually going up. It's going from -1 to 0. So this substance is being oxidized. This is the reaction that occurs at the anode. So anox, red cat. So by process of elimination, that means that the chromium is being reduced. But let's check. Chromium is going from 6 to 3, so its oxidation number is going down. It's gaining electrons, negatively charged electrons, to make the oxidation number go down. So this substance, yes, is being reduced, and this is the reaction that occurs at the cathode, red cat. So if you do this and you see that, both substances are their oxidation numbers are going up or both are going down, that means you probably did something wrong. The electrons have to come from somewhere. They will be produced at the anode and then they go to the cathode. So that's a way to check yourself that, something has to give up electrons, something has to gain electrons. So if you get both things are being reduced, that's not a redox reaction. Redox stands for reduction and oxidation. Okay, did we answer most of the questions? All right, yeah, basically most of them. So what's happening here, if you split up the reaction and actually write the half reactions here, does it want us to do that? Indicate the reactions occurring at the anode. So we want to write the balanced half reaction happening at the anode. So we just split this reaction up and make sure that it is balanced. So this is the oxidation reaction. So I'm going to take the species here, I minus and I2 here. I'm just going to rewrite it. So 6 I minuses go to 3 I2s. So that's not the balanced half reaction. We want to make sure that, the elements are balanced and the charge is balanced. So I see here the elements are balanced, so I can move on to the charge and recognize that you need to add 6 electrons to the product side in order to get both sides of the reaction to be -6. So remember, you always add electrons to make it charge balanced. And so since this side is already a -1 charge, you need to put 6 electrons on the product side. And that makes sense for an oxidation reaction. All oxidation reactions, the electrons are on the product side because that reaction is losing electrons. So electrons are being produced. So if you balance a half reaction, like an oxidation reaction, you have electrons on the other side, then you need to take a step back and relook at that to see if your atoms are balanced, and then take a look at charge again and revisit that if you have electrons on the wrong side. All right, so now let's do the reduction side. This is what's happening at the cathode. And so we take the other substances we didn't look at. So the dichromate substance, and we're producing 2 chromium 3 pluses. So note here, when we balance a redox reaction, when we go through the steps, we need to balance the elements. And so balance everything except oxygen and hydrogen. And so you see the chromiums are balanced. Then you balance oxygen by adding waters. So we need to add 7 waters here. And you can actually see this is all the leftover stuff in the reaction that I didn't put down yet. But we can, practice here balancing half reactions given what species are involved. So if I add 7 waters, I put 7 oxygens on my product side. But now we need to balance hydrogens. And so we balance hydrogens by adding H+. And so note here, there's 7 waters. So that means I need 14 H pluses on the reactant side. So now all the atoms are balanced, but now we need to balance the charge. And because there's a lot of species, take inventory of all the charges on both sides of the reaction. So there's 14 H pluses, so that's plus 14, but dichromate is a -2. So I recognize there's a plus 12 on the reactant side, and there's only a +6 on the product side because there's 2 chromium 3 pluses, and then water is neutral. So we balance charge by adding electrons. So in order to get these 2 numbers to match, if I add electrons, I want to bring 12 down to 6. So the last part of this balanced equation is adding the 6 electrons to the reactant side, and that is consistent with a reduction reaction. And note here, look, the electrons produced at the anode funnel the cathode. And so that is kind of the last idea here. The last question here is electrons are going to be produced at the anode because that's what's produced in the oxidation reaction. All right, you're producing electrons and they're going to migrate to the cathode. Right, cathode is positively charged, anode by convention is negatively charged. So electrons are going to move towards the cathode in order to do the reduction reaction here. And then the last question is, which way do the ions migrate when you set up this cell in your salt bridge? So this kind of has to do with the idea We're taking negatively charged iodide and we're making a neutral substance. So we need to make sure that the ion, the charge within your half cells stay charge neutral. So what we'll see here is that anions will actually migrate towards the anode, because what we're doing is we start with a negative charge, but that negative charge is being consumed because we're converting iodide to a neutral iodine. So anions want to replace every anion that is consumed in this reaction. And that's basically true for all redox reactions, that anions in the salt bridge, sorry, my thing is really being slow. In our salt bridge, the anions migrate to the anode, and then your cations actually migrate to the cathode in order for those solutions to be charge neutral. Another way to think about it, what did I write in my key? If you think about this reaction in the cathode, for every like 1 mole of dichromate that you reduce, you consume 14 H pluses. So there's a lot of positive charge there. And so kind of the same idea that cations are going to migrate to the cathode to replace all of those H pluses that you're consuming during this reaction, because you're consuming this 14 H plus, but you're only making 6 plus on the other side. So those cations will replace the positive charge that reduction reaction is consuming. And so that's true if you look at any redox reaction, that's how this would work. Anions migrate towards the anode, cations migrate towards the cathode. Okay, now I think this is done, this question. Okay, so let's do some calculations, I think, maybe. Yes, okay, so this previous question, I gave you the balanced redox reaction. You identify what is the cathode, what's the anode. What we didn't do is calculate the cell potential if this reaction was occurring at standard conditions. So when reactions are at standard conditions, we have table values of known reduction potentials, and we can put that together and calculate the total cell potential of the complete reaction. There's oxidation and reduction occurring. So how we calculate E cell for a full redox reaction is we take the reduction potential at the cathode, so this is whatever is being reduced, and we subtract the cell potential in the reduction form occurring at the anode. All right, so within here, it is in your best interest to identify, okay, what reactions happening at the cathode, what reactions happening at the anode. And then that's how we put together this equation. So here I'm giving you this reaction. It's happening at standard conditions because we have 1 molarity of all of the ions. So, and I give you the overall cell potential. So E cell is this number here. And so I give you the standard reduction potential of zinc. The problem is I don't know, is zinc your cathode or is it the anode? So we need to inspect the actual full redox reaction here. So like all redox reactions, we need to figure out oxidation numbers. So this one's a little bit easier because everything's pretty simple. Zinc is 0. Copper 2 plus is +2, zinc 2 plus is +2, copper is 0. So we can see that copper, its oxidation number is going down. So this is being reduced. This is the reaction happening at the cathode. And then our zinc person here, its oxidation is going up. So this is the, it's being oxidized. This is the reaction happening at the anode. All right, so now that piece of information is useful to us because now we know which one it goes into. So zinc, we're given the zinc reduction. So now we know that that's the reaction that is happening at the anode. So note here, when I put E not red, it means that you put the value for the reduction potential here, not the thing that's being reduced. So what I want you to recognize here, that it's cathode minus anode, and both of those values need to be in the reduction potential form because that's just how the convention of the table values are written within there. So if we now put in our known values. We are given that the E cell is 1.1, and we are given that zinc value, which is negative 0.76 volts. So we just put all of that together. All right. And so 1.10 volts equals the reduction potential happening at the cathode. And so the cathode is the copper couple here, minus the reduction potential at the anode. Oh, sorry, we know that number. All right, it is negative 0.76 volts. All right. And so again, I tell you what the reduction potential is, so you put it in here in the reaction as is, so that negative sign stays there. But in the end, we're subtracting a negative sign, so it does become positive. So when you calculate this, we see that the missing piece, the reduction potential happening at the cathode, so the copper couple is 0.34 volts. And so if you actually look up that value, that's the value that's on the table. And so the last thing here, yes, since it says give me the reduction potential of this reaction, that's what this equation is giving you. Remember, these two table values, they're all in the reduction form, even though at the anode, the thing is being oxidized. It's just by convention how this equation works. You want them both to be in the reduction form. Okay, so there, that one is just kind of a straightforward, like, given this information with E cell, figure out the missing piece for the overall reaction. Because in this one's a little bit different here. I give you two half reactions using the appendix, figure out which reaction occurs at the cathode, which one occurs at the anode, and figure out the cell potential. So I give you these two reactions. I give you parts of appendix E here. So I give you all of these are reduction potentials because all of these substances are being reduced. So we have this reaction is involving cadmium and tin. So I actually give you three different ones to trick you, to make sure that you use the right one. So note here that this reaction is tin 2 plus gaining 2 electrons. So we want to make sure that we use that one. So that would be this second equation, all right, that we don't use the third one here, because that involves tin 4 plus, not tin 2 plus. So don't use the wrong one. Did I use the wrong one? I hope I didn't. Yeah, no, I used the right one. Okay. So yes, don't use that reaction because it's not the right substance. So if we write the reduction potentials that are given, okay, negative 0.40 is cadmium and negative 0.14 volts is tin. So what we need to recognize with reduction potentials is that the more positive the value, the easier that substance will be reduced. And so we want to predict or set up our cell where it is the most spontaneous. So based upon these numbers, we see that the tin reduction potential is less negative. It's the most positive. Yes, they're both negative numbers, but the tin reaction is more positive. So to me, given this information, tin is going to be reduced, that this is the reactions that is happening at the cathode. And then our cadmium reaction here, because it is less easily reduced, it's actually better if we oxidize cadmium instead, and then we flip the sign of the reduction potential. This substance is going to be oxidized. This is what's happening at the anode. And so when we set this up and use our cell potential, overall cell potential calculation, cell potential calculation, that putting it this way will give us a positive number for our cell potential. And then that will be a spontaneous reaction. So the idea here is we want to identify our cathode and anode in a way that gives us the most positive cell potential. So E cell is going to be cathode minus anode. And we use those numbers. So we identified that our tin is our cathode, so 0.14 volts, minus the reaction we assigned as our anode, so the cadmium one, so negative 0.40 volts. And what you see is when you add up these two numbers, you do in fact get a positive number. So even though both of these reactions in the reduction form have negative cell potentials, because cadmium is very easily oxidized, it makes the overall reaction spontaneous because cadmium is pretty well oxidized and it can actually reduce our tin within here, even though it's not spontaneous. So setting it up in this way gives us the most positive value, so 0.26 volts. So if you identify it incorrectly, you will get a negative cell potential, and we should know that that is not a spontaneous reaction in that how that is written. Okay, so there we go. Cool. So it's just plug and chug, but recognize here how reduction potentials, can you set it up in a way to give you a spontaneous reaction? So positive cell value. All right, so this next question. So use the table that I give you the values here and calculate the free energy change delta G and the equilibrium constant at 298 Kelvin. So we already talked about how we calculate cell potential, all right? Cathode minus anode, but we also can relate cell potential to Gibbs free energy. I already kind of talked about this, that a positive E cell value gives you a negative delta G value, because in chapter 16, we already talked about negative G values, negative Gibbs free energy. Those are spontaneous reaction when free energy goes down, when your system becomes more stable in terms of energy or enthalpy and entropy. So these two pieces of information are related to one another by a new equation we represented in this chapter. Delta G naught equals negative NF E cell. All right, so your cell potential times all this stuff times a negative number gives you delta G. So you can see here, if E cell is positive, delta G is negative because we have this negative sign. So again, that's pointing to the idea that positive cell potentials are spontaneous because you get a negative delta G value. But if E cell is negative, then you take a negative times a negative, delta G is positive. It's not spontaneous in that direction. So that's the new equation here, but this question also wants you to calculate K. So if we recall from chapter 19 and where K comes from, it's actually related to delta G. So in chapter 19, we talked about delta G equals negative RT ln K. So if we know E cell, we can calculate delta G. That's part of the question. And then we can go one step further and plug it into this equation to get K in that case, because we know the temperature. So let's actually do this. So I give you the whole reaction here. So again, like all redox reactions, we need to get those oxidation numbers, figure out what is the cathode, what is the anode, and make the right subtraction. So silver is going from 0 to +1. So silver is being oxidized. That's the anode. And then H plus is +1, and it's +1 in water. So that doesn't change. We can ignore it. But oxygen is 0 is as O2 because it's in its elemental form, but it's -2 in water because it's in a compound here. So we see that oxygen is actually, its oxidation number is going down. So it is being reduced. It is the cathode. All right. So now we can calculate our cell potential given those table values because we know what's being oxidized and what is being reduced. So E cell is cathode minus anode. So our cathode we said is oxygen. So that is this number. Okay, the second one, the oxygen reaction. So 1.23 minus what's happening at the anode, which is the silver reaction. So minus a positive 0.80 volts. All right, and so we get a positive number here that the overall cell potential is positive 0.4043 volts. That is our standard cell potential. And it's a positive number, meaning that this reaction is spontaneous. So that's good. All right. So we have that. We have the cell potential. So this is what helps us give us our Gibbs free energy for this reaction. So delta G naught equals negative NF E cell. So we have E cell. F is a constant. We just need N in this case. N is the number of electrons that are transferred during this reaction. So if we go back to the actual reaction here, all right, silver is going from silver 0 to silver plus. So it is losing 1 electron, but the thing is that there's 4 silvers involved here. So there's a total of 4 electrons being lost. So I recognize that N equals 4 here. You could split it up into half reactions and inspect it that way. That's like kind of my little cheater way to do it. All right. So N is equal to 4. Here, if you just inspect the oxidation numbers and how many actual particles are involved, or the coefficients involved in the reaction. And now we just plug in all the numbers. So delta G equals -4 times Faraday's constant. So 96485. And then the cell potential we just got, so 0.43 volts. And so what we get here is our Gibbs free energy, and this will be in the unit of joules. That's what basically, if you look at the SI units of Faraday's constant, a joule comes out of here. And so you see that the Gibbs free energy is negative 166 times 10 to the 3 joules per mole here. So negative 166 kilojoules per mole. And again, that negative sign is important because that has to be consistent with our spontaneous cell potential. We need a negative delta G value. And so the next part of this reaction, or this question, says calculate the equilibrium constant K. So now we just have to plug in that delta G value we just got into the K reaction that relates equilibrium constant to Gibbs free energy. So we know delta G, R is a constant, T is given, it's 298 Kelvin. So all we do is just plug in that number we just got and plug it in or solve for K in this case. So this equation that I just wrote in green, this is from chapter 19, where we talked about thermodynamics within there. So you calculate K. K should be a really, really large number because this reaction is spontaneous in the forward direction, meaning you form a lot of products. So K should be really large. K is products over reactants. So K should be large. And so when you get that, I think you get K. Yeah, it's a huge number. It's 1.2 times 10 to the 29. It's a huge number, right? And so the last part of this question says, okay, suppose the reaction is written. So if I kind of look at this, it looks like this reaction is divided by 2. All right, we're now, okay, what if we rewrite the question here? What are the values for E cell, delta G, and K when you write it this way? So if we look at kind of our work here, when we calculated cell potential, it didn't matter like how many electrons or how much of each substance is being oxidized or reduced. We just locate their half reactions, the reduction half reactions here, and do the subtraction. So what you'll see here in part B, what they want you to think about is if we change the coefficients of the reaction. So like kind of like Hess's law, like divide it. E cell actually doesn't change because all we're doing is identifying what is the cathode, what is the anode, and we subtract those those reduction potentials. So E cell does not change. But what does change is N. So if we divide the reaction by 2, instead of involving 4 electrons in this reaction, we actually only involve 2 electrons. So what does change is delta G. All right, so if we change delta G, our new delta G value for this second reaction will just be the answer we got, but divided by 2. And then when we calculate K, because delta G changed, K changes as well. So delta G and K will change in this case, but I'm not going to do the work, just basically do all this work again, but change this 4 in for 2 instead, because we divided the reaction by 2. Do you put delta G in kilojoules or joules? You always put in this reaction in joules because the unit of R is 8.314 joules per mole Kelvin. So delta G needs to be in joules. So when you plug your cell potential into this initial equation, you get delta G in joules. And so you just plug in that number straight away as is into this equation. Again, it's dictated by the unit of R, which is joules. All right, so I'm not going to do the work here. You can see the key that those things do change. but not E cell because there's no dependence on N. Divide by 2 or so the idea, so you don't divide K by 2. The idea here is delta G, the new delta G value is divided by 2. But how we calculate K is we use delta G from the previous step. So this number is divided by 2 doesn't necessarily mean K is divided by 2. Actually calculate it with the new value. And you'll see that K doesn't change by 2. It actually changes by a square root. I'm not sure how it changes, but because it's inside a natural log within there, it changes differently. So just calculate for K again with that new delta G value. You can see that in my key. I just used the new delta G value and plug that in and calculate for K. Okay, so let's keep going. How many more do I have to do? Okay, 2 more. Okay, so the next one. Let's calculate the cell potential of this reaction given these conditions. So EMF, okay, means cell potential. That's all it means, cell potential, whether it's standard conditions or not standard conditions. So in this case, because if we look, I give you concentrations of these things, that means we're not at standard conditions. So we need to use the Nernst equation in order to answer this question. But the Nernst equation, all it says is that the measured cell potential is equal to the cell potential at standard conditions minus the concentrations of stuff that is actually there. So we have to calculate Q because we're not at standard conditions. So that's why we use Q in this case. So Nernst equation is 0.0592 volts over N. So this numerator part of the Nernst equation takes into account temperature and Faraday's constant because most of these reactions happen at this 298 Kelvin. But temperature, you can account for temperature in the Nernst equation. You just have to use its form that has the actual variables in it. This is just the way we present it to make it a little nicer to look at. So negative log Q. So that's the Nernst equation. You're given that on the exam. So recognize here what we need in order to calculate EMF. EMF is our E cell at not standard conditions. So the pieces of information we need are the cell potential at standard conditions. We need to figure that out. We need to figure out what N is, and we need to figure out what Q is. So let's recognize that Q comes from the concentrations that are given. N comes from the number of electrons that are involved in this reaction. E cell not comes from us identifying what's being oxidized, what's being reduced. So I think we already did this reaction, right? The oxidation of iodine, but let's just do it again. Chromium was +6 in dichromate, iodide is -1. Chromium 3+ is 3+, and then I2 is 0. So what we see here is that iodide is being oxidized. That's our anode. And then chromium is being reduced. That is our cathode. So by identifying what's being oxidized and reduced, we can get our cell potential given the half reactions that I put here for you. So remember, E cell is cathode minus anode. So we take the cell potential from the chromium thing there, so 1.33 minus what's happening at the anode, so 0.54. And we see that the cell potential at standard conditions is 0.79 volts. We would measure that value if we had 1 molarity of everything. 1 molarity dichromate, 1 molarity H+, 1 molarity I-, 1 molarity chromium 3+. That's what our cell potential would be. But the problem is that we don't have those concentrations, right? So we don't have 1 molarity of everything. So we need to account for Q in this case. But actually, before we move on, let's figure out what N is before we get too far. I don't feel like truly like looking at the half reactions. So what I recognize here, I'll focus on iodide. I see that iodide is a -1, all right? And then it's becoming iodine. which is neutral. So that means to me, 6 electrons are involved in this reaction. So that's kind of the cheater way that I do it. 6 electrons are involved here. That those 6 iodides are losing 6 electrons to make 3 neutral iodines. If you go back to the first question in this section we did, you'll see that in order to balance it, we needed 6 electrons, but that's just my cheater way to do it. So N equals 6. We'll need that when we plug into Nernst equation. So that's N. Now we need to get Q. And so Q is based upon how we set up K, products over reactants. So we need to get those, the expression for Q first. So we take the concentrations of the reactants, so chromium 3 plus squared, because there's a 2 coefficient here. So this is where we take into account coefficients. Note that in the cell potential, we don't care about how many of the things are involved, but where it does come into play is Q. So chromium concentration, I is a solid, so that doesn't have a concentration. Water is a liquid, doesn't have a concentration. So then let's look at the reactants. We have dichromate. Okay, there, and there's just one of them, so no exponent. We have H plus to the 14, so an exponent to the 14. And then we have I minus, also, all of those have concentrations, and it's to the 6th power. And so I'm going to just plug in those numbers that the question gave us so we can get Q and plug it into the Nernst equation. So chromium 3 plus is 1 times 10 to the negative 5 molarity. That's our numerator. And then our denominator, dichromate is 2.0 molarity. To note, oh, that's squared, sorry. And then hydrogen, H plus, is 1 molarity. And it's to the 14, so it's just 1. And then iodide to the 6th, also just 1 molarity. All right, so all of those values, yes, they're big subscripts, but big superscripts, but it's just 1 times 1 14 times. All right, and that's just 1. So when you calculate this, you're just doing 1 times 10 to the negative 5 over 2, or to the 2nd, over 2 molarity coming from dichromate. So what you see here is that Q should be a fairly small number. Yes, it's a fairly small number. So 5 times 10 to the negative 11. That is Q. So in my mind, that at these conditions, we don't have a lot of product yet. We have a lot of reactant. And so my idea is, if this reaction is spontaneous in the forward direction, there's a lot of potential pushing this reaction in the forward direction. So my intuition tells me that this measured, the actual cell potential, is going to be higher than from standard conditions, because we have a lot of reactants present instead of products. But that's just kind of, using my intuition there. But let's actually plug in this Q value and see what we get in the Nernst equation. So we have E cell equals our standard cell potential minus 0.0592 volts over N log Q. So now we have all of those pieces of information we didn't have previously. So cell potential at standard conditions is 0.79 volts minus 0.0592 volts over N, which we got is 6, times log of 5 times 10 to the negative 11. All right, and so when you calculate that, you get that the actual measured cell potential at these concentrations that aren't standard conditions is actually 0.89. So I was right, that the cell potential, the measured cell potential, is a little bit higher than from standard conditions because we have so much more reactants present. If it were the other way, if we think about this, if this reaction is only spontaneous in the forward direction, if we have mostly products and no reactants, so K is large, Q is large, that means that your battery ran out of juice, that you converted all of your reactants to products, and now there's no more potential energy to harness for your battery to run, because essentially what this is a battery. You ran out of juice there, that you converted everything to products, you harvested all the energy that you could already when there's a lot of products, versus when you have a lot of reactants, then you have a little bit more juice to push that reaction forward. All right, so that's how the Nernst equation works. So the Nernst equation, you use this when you are not at standard conditions. So note when if you have a reaction at standard conditions, and you set it up, you will measure this cell potential. But as it moves forward, that cell potential is going to get smaller and smaller and smaller and smaller, because what takes over is the Nernst equation. Because as the reaction's moving forward, you're changing Q closer to 1, not closer to 1, closer to K in this case. Once your Q value is really high, meaning that you form a lot of products, your cell potential, measured cell potential, E cell without the knot, gets closer to 0, that there's no forward potential pushing this reaction forward. So there we go. Oh, we already did this question. So yeah, so this is the last part of electrochemistry. So all of those other reactions, we looked at spontaneous reactions, meaning that cell potential was a positive number. They're spontaneous. We call those voltaic cells, or also older textbooks say galvanic cells. It means the same thing. It means spontaneous cell. E cell is positive. The idea is, well, if electrons aren't created spontaneously in a reaction, we can just plug the reaction into the wall and supply electrons ourselves. And so we do that by measuring amperage coming from the wall. Amperage, the unit of amps, also means a coulomb per second. And so because we know how much charge comes from a mole's worth of electrons, that's Faraday's constant, we can figure out how many electrons we supply to a chemical reaction if we know the amperage and if we know the time. And so in this question, I want you to tell me the amount of grams of aluminum that we produce in 1 hour by electrolysis of molten aluminum chloride at this current. So this aluminum chloride is Al3+ because it's ionic. So we need to give it 3 electrons in order to turn it into a solid. And so this is stoichiometry, but we use the idea that an amp is a coulomb per second. So 10 amps, 10 coulombs is supplied per second. So if we start with the time, we can go through here, convert hours to seconds, and recognize, okay, if we have coulombs, you know how many coulombs we deliver, use Faraday's constant and recognize that 1 mole of electrons requires 96,000 coulombs. Now we know how many moles of electrons we delivered, and then use the stoichiometry here. We need 3 electrons per every mole of aluminum, and then just use the molar mass. So the big idea here is that amperage means coulombs per second, and that we need to use Faraday's constant to go from the Coulomb realm to the electron realm. And then we need the balanced equation to figure out how many electrons do we need to supply to the thing to turn it into a solid, a neutral solid here. All right, so there we go. There we go. So that is electrochem. We have 35 minutes left. What question do you want me to do from the rest of the packet? Does someone... Can we do 23.5? I did that in class, so just look at the video. Oh, wait, no, we didn't. We didn't do that in class. Do we need to know how to read line notation? It's in your best interest to know line notation, but just know that it's the anode, the reaction at the anode, and then it's the reaction happening at the cathode. All right, so it's like when you draw your cell. You know, you draw your cell. Typically, you draw the anode over here. Anode, cathode. So line notation tells you exactly what's happening at the anode, exactly what's happening at the cathode. Okay. Yes, let's do 23.5. Yeah, no, I didn't do that one in class. Whoops. Yes, okay, so let's do that one. Okay. So this is the last one within the new chapters. I forgot about this one. Within the new chapters that hasn't been assessed previously. Okay, so let's look at cis and trans. These substances, do they have optical isomers? Did I do it? No, I didn't. No, this was just me talking with a student. Okay, so recognize here. So let's do this in completeness. Let's do this reaction in completeness. So let's look at these 2 substances. They are isomers because they have the exact same chemical formulas. En stands for ethylene diamine, which is a bidentate. that it binds to your metal center twice in 2 spots, versus chloride is a monodentate. It only binds once. So if we look at these compounds, there's a couple things we can look at. We can determine what is the oxidation number of cobalt given this substance. I tell you the charge, and we should know the charges of common ligands. Ethylene diamine is neutral. Chloride is a -1, but there's 2 of them. So I recognize that there's a -2 charge coming from chloride. I need a +1 overall charge for this substance. So that means cobalt has to be cobalt 3+. So there's one question I could ask you here. And then it's the same, cobalt's the same charge in this one as well, because they're isomers. Another question I could ask you is how many D electrons are on cobalt 3+. So it requires us to look at the periodic table. I recognize cobalt is the 7th element in the D block. It has to lose 3 electrons. The first 2 electrons are going to come from the 4s subshell, and then we'll lose 1 D electron. So cobalt 3+ is D6. All right, when it loses 3 electrons. So those are some questions. Another question is to ask, what is the coordination number of this substance? So we need to look at what things are actually bound to cobalt. So recognize that there's 2 chlorides. Both of those chlorides are monodentate, right? And this is just something you need to memorize, that there is a table of common ligands, right? What the monodentates are. A lot of them, it's like one atom, but there's lone pairs present somewhere. And so those lone pairs is what makes the dative bond to the metal center. So those are monodentates. So that takes into account 2 of the coordination sites. Ethylene diamine, there's 2 of them. This is a bidentate. All right, bidentate, because when you write out ethylene diamine, there's a nitrogen, and then there's like a carbon, and then there's another nitrogen. All right, and these are hydrogens. So essentially what ethylene diamine is 2 ammonias that are connected to one another. They're connected to one another via a carbon chain. So when you have one ethylene diamine molecule, it actually can bind twice to your metal center. So when there's 2 ethylene diamines, there's a total of 4 coordination sites that are being occupied by those 2 ethylene diamines. So there's a total coordination number of 6. This is equal to an octahedral. All right, so there's common bidentates, ethylene diamine, bipyridine, carbonate, oxalate. Those are common bidentates. So recognize, if you looked at this like really quickly, you might say, oh, the coordination number is 4. There's 4 things attached to it. But if you say 4, that means you ignored the fact that ethylene diamine is a bidentate. So there we go. All right, so that is the coordination number. So that means that both of these compounds have a octahedral crystal field. All right, that they look like this. They look like an octahedron. So 6 electron domains around it. So the idea is, well, okay, how can we draw these different isomers? We can draw the cis version, where the chlorides are cis, they're next to one another, or we can draw the trans version, where there's chlorides are opposite of one another, trans to one another. So let's draw the cis version first. So the cis version of this compound, I'm going to put a chloride right here and right here. It doesn't really matter. They just need to be next to each other. So that means that the ethylene diamines have to occupy the other sites, the other 4 sites. So I will just draw them like this. Remember, these are bidentates. So those ethylene diamines, so I'll put the nitrogens, right? Like this, nitrogen, like that. All right, they're connected to one another because this is a bidentate. So this is the cis version. How I recognize it is I notice that those chlorides are next to one another. They are cis to one another, versus the trans version of this molecule. So these are their geometric isomers, because cis and trans are geometric isomers, still considered stereoisomers, meaning that the atoms, the bonds themselves, differ in 3 dimensions, but they're still isomers nonetheless, because it's still 2 chlorides and 2 ethylene diamines and a cobalt. So they're still isomers, but they're geometric isomers because their ligands differ in 3 dimensions. So what this trans version looks like is, again, I'm going to focus on chloride, and I want to place the chlorides so they're opposite of one another. So I'm just going to put them here instead. So note how this looks much different than this in respect to where the chlorides are. So these chlorides are trans to one another. So I still need to place those ethylene diamines. So I'm going to place one right here and one right there. So these are completely different molecules. These are geometric isomers. They're completely different. They'll have different properties. So I've drawn the cis and trans version. So now the question is, do either of these have optical isomers? Meaning, do any of them have non-superimposable mirror images? So the best thing to do is draw their mirror images and see if I draw the mirror image, are they the same molecule or not? Meaning, are they superimposable? So the strategy here is, if you draw the mirror images, the trans version, when you draw the trans version, how would that look? Like this, okay, like that, and then like that, and then we draw the chlorides like this, and then we draw the ethylene diamines like this. Right, so that's the perfect mirror image. I tried my best to like mimic, the wedges. They're being mirrored. The dots, they're going into the page being mirrored. These are actually the exact same molecule, right? They're the exact same molecule. The reason that they're the exact same molecule is because if you look at the trans version, there's already a mirror plane in the molecule. The mirror image of a mirror is always the same. You get the same thing back. So how I recognize when something does not have a chiral center is if there is symmetry in the molecule already. If there's symmetry, then it's not chiral. So for example, if you put a mirror basically on the plane of where the ethylene diamines are, you would mirror those two chlorides opposite of one another. So that's where there's actually many mirror planes, but there's one of them. So these are not mirror images. They are actually the exact same molecule, because the mirror image of a mirror, you always get the same thing back. So are the same, meaning that the trans version does not have an optical isomer, because optical isomers, you need two different non-superimposable molecules, not have optical isomers. So what differs is our cis version, because if you do take the mirror image of this molecule, I'll try my best to draw the mirror image. Okay, there. These are actually not superimposed, or sorry, yeah, they are not superimposable. They are different molecules. The fans are twisted in an opposite direction. This is tough to see for a lot of students. I'm just going to tell you that the criteria for optical isomers with octahedron are if you have the bidentates. You need 2 or 3 bidentates, and they have to be in the cis configuration, like you see right here. If there's two bidentates, so that's the criteria you need for an octahedron chiral molecule. I have that up in my slides somewhere. But if there's 3 bidentates, it will always have optical isomers. That is the chiral center if there's 3 bidentates on an octahedron, because you can think of it as like fan blades on a fan. So what we see here is, if I rotate this molecule to try to make these two molecules match, right, with the chlorides in the same space, what you'd see is that in one of the molecules, this fan is pointing forward. If you did it for this molecule as well, this fan in this position is actually pointing backwards. And so again, they are not the same molecule. So the answer here is only the cis version has an optical isomer. Because its mirror image is not superimposable, that they are unique molecules. All right, they will have unique properties. All right, and so optical isomers here with octahedron, we usually use notation such as lambda and delta, but that is not important for you to recognize and like identify which one is lambda and delta. What I want you to know is that these two molecules are different. They are not the same molecule, but these two are. Okay. explain the chelate effect. The chelate effect, is it not in here? It's the idea of why the chelate effect, it basically explains why when we take like a metal, so like a cobalt something, all right, and we add 3 ethylene diamines, all right, why this substance forms really readily, all right? The reason that this forms really readily, you can think about it in two steps here. We can think about the enthalpy component and the entropy component. So if we look at this reaction and compare it to something like, instead of ethylene diamine, we instead connect ammonia, 6 ammonias instead, because ethylene and diamine is essentially just 2 ammonias just stuck together. So if we compare it to this reaction, both of these reactions have K values associated with them. But what we see by observation is that in the chelate effect, K is really, really large when a bi or polydentate is involved. K is large. That is what explains the observation we make about the chelate effect. So why K is really large is because if we look at the delta H component of these two reactions, they're actually very similar because we have the same bonds being broken, we have the same bonds being formed. But what's different is the entropy of these reactions. Remember, delta G equals delta H minus T delta S. So if we look at these two reactions, if we look at this one, we have 7 things on the reactant side, we have 7 things on the product side. So delta S is going to be around 0. That the entropy, the number of particles aren't really changing. But if we look at the chelated version, we're going from 4 things to 7 things. So I see that delta S is actually going to be quite a big positive number. And so what we see here is that if we compare the delta G's of these two reactions, the Gibbs free energy at the same temperature, the delta H is going to be the same number, but entropy is different. So in the chelate version, delta G is going to be more negative because delta S is a larger positive number. And so if delta G is negative, if you remember, delta G equals negative RT ln K. If delta G is very negative, K is going to be a large number. So it's the positive entropy value that you get for the chelate effect gives you a more negative delta G value, gives you a larger, more positive, or like a larger value of K. So that's how that works. Okay, we have 22 minutes. Is there another specific question now from previous chapters? So wow, it took us a long time to do all the new stuff. Any specific questions for older chapters? Older chapters. If no one says anything, then I'll just end early. If no one has a suggestion for a problem, I'm going to just end early. Can I explain the difference between small k and big K? Yes. Small k is rate constant. Small k, I give myself another page. Yes. Small k is rate constant. Big K is equilibrium constant. Equilibrium constant, we always said, is roughly equal to the concentrations of products over the concentration of reactants. But this is just kind of like my cheat way in order for us to, figure out the magnitudes within here. So rate constant, the small k, tells us how fast, forward and reverse reactions go. So we learned about this first in chapter 14 when we talked about chemical reaction kinetics, that based upon the reaction coordinate, if we have reactants over here and products over here, your rate constant is related to your activation energy from, forward to reverse. But the thing is, when we have a chemical equilibrium, we have a rate in the forward direction is equal to the rate in the reverse direction. So one of the ways we think about k, small, so rate constant, is the Arrhenius equation, where we can kind of think about the magnitude of how fast a reaction moves forward is based upon its activation energy and RT and the temperature at which the reaction goes, that you set your reaction at. That K will change if you heat up your temperature, that your reaction will go faster in the forward direction if you supply more energy, more heat to the reaction. That K will increase if you give it more energy. Another way K can change is if we change the activation barrier to go from one side to the other. If we make the hill smaller, then yeah, more particles will be converted to products. So what we see here based upon the Arrhenius equation is that K will increase when activation energy gets smaller or when temperature increases. So that's rate. Equilibrium constant comes into play with the idea that at equilibrium, the forward rate, what am I doing? Come back. What's happening? Okay. At equilibrium, the rate in your forward direction, so forward, equals the rate in the reverse reaction or the reverse direction. All right. So what we're saying, if this reaction was at equilibrium, there's a rate going forward, there's a rate going backwards. But at equilibrium, what's unique about equilibrium is that the net rates in those both directions, they cancel out with one another. So you don't see any change in concentrations of reactants and products. So this is the idea of our equilibrium constant. And the idea of equilibrium. So the idea of, rate, also, we can actually write the rate law for these substances. So instead of rate, when I write rate, it's not equal to K. This does not equal K. The rate law is the overall rate of the forward reaction equals K, small k, some rate constant times concentrations of your species involved. So what we see here when we talk about the rate in the forward direction, that we have a K value, the K rate constant in your forward direction times the concentrations of reactants equals your reverse rate constant, because your reverse rate constant is going to be a different value, reverse. The K for the reverse reaction, excuse me, is a different value because the activation energy is a different value. So note here, remember the effects on K depend on activation energy. So large activation energy, K is actually going to be smaller for the reverse reaction. So, but the same idea here, if this reaction were to go in reverse, the products are now your reactants. Those are the species that are being involved here. So you have concentrations of products. So if we rearrange things, what we get, so if I divide K reverse on both sides, all right, and I divide by reactants on both sides, reactants, okay, what I get is that K forward over K reverse equals concentrations of products, concentrations of reactants. All right, so this ratio that came from the idea at equilibrium, forward rate equals reverse rate, we get that our rate constants, the ratio of our rate constants equals the ratio of products over reactants. This is big K. right? So big K is dependent on the magnitudes of your rate constants in your forward and reverse directions. These values should be different. They should be different if we have like an exothermic or endothermic reaction. It all has to do with the differences in activation energy. But what we get here also is that K is also equal to the ratio of products over reactants at equilibrium. This is the one that we use more often for calculations, but do recall that it has to do with chemical kinetics as well. You know, which direction of the reaction is more favorable. If it's easier for reactants to get to products, then you're going to have a lot of products present at equilibrium. So that means that the rate constant for the forward direction is large. Both of those things give you a large K value. Lots of products means forward direction of your reaction is very favorable, very large. And again, that has to do with our like our diagram here. That would be true for this example, this exothermic reaction, because the activation energy is smaller in the forward direction versus larger in the reverse reaction. So what we see here is that the rate constant for the reverse reaction is going to be small. Okay, so there we go. Okay, K and big K from chapter 14, writing the expression, does the coefficient become the exponent? So chapter 14 is chemical kinetics. So remember when we came up with rate laws, the coefficient only becomes the exponent if it is a, what is that word? Oh crap, I forgot the word. An elementary reaction. If I tell you it's an elementary reaction, then the reactants, like the number of reactants there, become the exponents. Those exponents are based upon order. So like first order, second order, you know, zero order. Typically order of reactions is determined experimentally. So that's like examples like one where I give you like table values here, okay? Like table values, or like experiments where you need to determine what is the order of the reaction. I mean, like oftentimes when we look at a reaction like this, you might think, oh, this is first order in A, first order in B, but that's not true because this is not an elementary reaction. We actually have to determine it experimentally. But if I give you a reaction like this, and I tell you that these are elementary reactions, this is the mechanism for this reaction, then yes, the coefficients do become the order, the superscripts or the exponents there. So this would be first order for this you know step is first order in N2O. And it would be the rate of this reaction would be N2O times the concentration of oxygen here. So in this reaction, where we determine the rate law for a multi-step mechanism, the slow step always dictates the overall reaction. So the overall rate law for this reaction would just be K of the first reaction times the concentration of N2O. So this reaction is first order, that the components of the second reaction don't matter because we're assuming that this happens basically instantly. The overall rate of the reaction is dictated by the slow step. So the overall rate of this reaction is just, if I call this K1 is equal to K1 times N2O. I can only do this because this is an elementary step. I cannot do that for this reaction because I didn't tell you it's an elementary reaction. I actually give you data for you to figure out what is the overall rate law. Okay, there, that, okay, 14.15. 14.15. Oh, perfect. Perfect. So I just talked about, you know, this reaction, that the slow step always dictates the overall reaction, overall rate of the reaction. So in this one, the slow step is the first step. So it's easy, right? That the rate of this reaction is just dependent on the concentration of N2O that you start with, because that is the limiting, basically like the limiting step. Every time that this reaction does go forward, the whole reaction will like proceed. And then that's the overall reaction rate. So that one's easy. So yeah, that's the rate law for this overall reaction. It's a little bit more difficult when the slow step is not the first step, all right? So in this example, we're still going off the fact that the slow step always dictates the overall reaction order. So let's do that. If you do that for this reaction, you see that the rate, so this is slow. So we're saying, okay, step 2 is what's dictating the overall reaction rate. That rate equals K2 times N2O2 times Br2. What's concentration of Br2? Okay. Oh, come on. The problem with this is that N2O2 is an intermediate, that I can't actually control the concentration of this intermediate. I need to make sure when I write my rate law, it only contains components that are species within the overall chemical reaction. So I didn't do that. If we wanted to get the overall chemical reaction here, we would add up these two reactions and you would recognize N2O2 is a intermediate. It's produced, then immediately consumed. So the overall reaction, if you just add up these two reaction, is 2 NOs plus Br2 gives you 2 NOBr. That's the overall reaction. So I need to make sure when I write out my entire rate law that it only contains things in my reaction. N2O2 is an intermediate. So I think if you look at my key, I say not allowed. It's not allowed. N2O2 doesn't belong in the rate law. So we need to get rid of it. And the way we get rid of it is we look at the first step, which is an equilibrium. It's a fast equilibrium. So we will use that equation to help us get rid of that intermediate in our rate law. So if we look at step 1, this is an equilibrium, meaning that the forward rate, so the rate in the forward direction equals the rate in the reverse direction. And so since these are elementary reactions, we can say K1 times the concentrations of the reactants is equal to your forward rate. Again, we can only say this for elementary reactions. So the forward rate is just K1 times the concentration of the reactants. It's NO, but there's 2 of them. So it's NO squared, or NO concentration squared, times the reverse, or equals the reverse rate, which is equal to the rate constant for the reverse reaction. So we call that K-1, times the concentration of N2O2. That is the product, right? So it's the concentration of products is what's dictating the reverse reaction. So converting products to reactants. So using this idea, you can isolate N2O2, all right, and rearrange this equation to get some type of expression that you can replace in the original rate law equation where N2O2 is present. So if I rearrange things here, you get that the concentration of N2O2 equals K1 over K-1 times NO squared. So I'm going to put this and replace N2O2 with this new expression, and that is my overall rate law. So it will be something like rate equals some K value, so K overall. That K overall is just the multiplication of all those K values. We can't really discern the specific K values. What we'll actually observe is just some overall value. And so what you get here is that NO squared, 2 of them, times bromine, 1 of them. So it's second order in respect to NO, but first order in respect to Br2. So that's how you approach a slow second step type of reaction. That, again, slow step dictates the overall reaction rate, but you need to make sure that there are no intermediates there. So you might have to use the fast equilibrium step to get rid of that intermediate. And so the last part of this question says, does this mechanism, is it consistent, like us dictating that the slow step is the second step. Is it consistent with the experimentally determined rate law? So we got second order in NO, first order in BR. So if this is the experimentally determined rate law from the book, I took all these from the book, yes, that the mechanism is consistent with the experimentally determined rate law. Remember, this is overall. All right, so that would mean that this person, conducted this reaction with different initial concentrations. They tracked the initial rate of product being produced, and were able, by varying initial concentrations, to get the overall rate law. And so what we see is that rate law is consistent with the steps of this proposed mechanism. Okay, so there we go. Five more minutes. Do an example of ranking compounds with freezing point and stuff. Cool. Yeah, I can do that. Is there an example here? Is there an example here? No, there's not. Okay. So, the idea in solution chemistry, okay, the first chapter we talked about, where when we dissolve a solute in water, we're actually changing the vapor pressure of water, because the idea that the vapor pressure of water that it exerts is equal to the mole fraction of water times the pure vapor pressure of pure water at that specific temperature. So the idea here is, if you had pure water at room temperature, it exerts something like 28 torr or something. But the idea is, if you start adding a lot of salt or a lot of some other thing, you're changing the mole fraction of water that is present, because you're adding other stuff. So this number, X mole fraction, is going to be less than 1. So when we think about colligative properties, when you add solute, vapor pressure of your solvent actually goes down. It's vapor pressure lowering. And so what we see is vapor pressure lowering with colligative properties. Freezing point temperature decreases as we add more solute, and boiling point temperature increases. So let me just write that. What did I just say? As you increase the amount of solute, so let's say we just add salt or something, what we'll see is that the mole fraction of water or your solvent actually goes down. What you also see is that the vapor pressure of above the water also goes down, because X, your mole fraction, goes down. We see that freezing point temperature also goes down, but we see boiling point temperature actually go up. And so we can calculate things like freezing point temperature, boiling point temperature, based upon the molality of the solution. So if we look at freezing point temperature, the change in freezing point temperature equals the freezing point temperature constant for that solvent that's typically given, times, oh wait, how's it usually written? Something like this. Okay, negative IM, and then the freezing point constant, that's typically for that solvent. So the idea here is that it depends on how much solute is present in your solution, where M, molality, equals moles of your solute over kilograms of your solvent. So M will increase when you increase the number of moles of stuff you dissolve. But what we also see is that this number, delta, the change in freezing point temperature, also its magnitude gets larger if you dissolve more particles. So I, the Van 't Hoff factor, has to do with the number of particles that you actually get when you dissolve a substance. So for example, like CH4 is a molecule. So if you dissolve that in water, you would only get CH4 aqueous. So I equals 0, or sorry, not 0, it equals 1. For every 1 molecule of CH4 you dissolve, you only get 1 CH4 aqueous out of it. Same thing with sugar, glucose, it's a molecule. So for every 1 molecule you dissolve, you only get 1 molecule, neutral molecule, floating around. Where things differ is like something like salt. If you dissolve NaCl solid, right, and you have a certain number of moles of NaCl you dissolve, you actually get Na plus and Cl minus. You get a 2-for-1 special. All right, you get, for every 1 molecule or 1 formula unit of NaCl you dissolve, you get 2 particles out of it. So your Van 't Hoff factor equals 2 instead. So you get twice as much freezing point lowering for NaCl versus a molecular substance. So like, I don't know if I told the story that back in Pennsylvania, where I'm from, they tried to put sugar on the roads, like a byproduct of like the chocolate factories or something there. They tried to spray sugar on the roads to lower the freezing point to prevent ice from forming on the roads, but it didn't work very well because, again, the Van't Hoff factor is 1 versus salt, like rock salt, it has a Van't Hoff factor of 2. So it's going to be twice as powerful for every mole of stuff that you dissolve versus something like calcium chloride. All right, when you dissolve calcium chloride, you get calcium 2 plus and 2 chlorides. So your Van't Hoff factor is 3. So if you want really, really good freezing point lowering to protect, and prevent icy walkways, those folks will use calcium chloride on the roads to prevent to be used at really, really low temperatures because it has a higher freezing point depression, magnitude within there. So when looking at these substances, they differ in terms of their I value. That calcium chloride has the most freezing point lowering ability because its I is 3. So if all of these solutions had the exact same molality, all right, the same concentration, essentially, that calcium chloride is going to have the most freezing point lowering because of I is different. But again, both of these things multiplied by one another give you the results of freezing point lowering. So you need to consider I and its molality presented within there to figure out, okay, what has the lowest freezing point thing. All right. And then the idea of ion pairing happens that, yes, these are Van't Hoff factors 1, 2, and 3. But the idea for ions is that the Van't Hoff factor experimentally is slightly lower than 2 and 3. And it's due to things like very high charges or very high concentrations that I kind of deviates a little bit. All right. And so look at some examples from like overview packets to look at rankings there from chapter 13. All right. Okay. So that's it. Thanks guys for staying with me. I'm going to stop recording.